Now, this is the second method. We can calculate the potential energy of an electric dipole in a uniform electric field. Why the second method is needed? Because in the first today's session, I have explained what is the potential energy of a two-charge system in an external field. So using that formula, we can also derive here. See, I have taken a uniform electric field E here. I have taken an electric dipole and a dipole moment and electric field. The angle between them is theta. Clear? We can use this equation, like the equation what we have taken for a two-charge system in a uniform electric field. See, the equation will give you, see, that formula is, what is that formula? That formula is, this is given by U is equal to V1 Q1 plus V2 Q2 plus 1 by 4 pi epsilon naught Q1 Q2 by R. The same formula I have applied here. U is equal to V1 Q1, V2 Q2 plus 1 by 4 pi epsilon Q1 Q2 by R. This formula. V1 means potential here. That is your V1 I have mentioned here. Q1 is the magnitude of the charge, which is plus Q. Q I have written here. V2 into Q2, that is V2 is the potential here. Q2 is what? Minus Q, because the charge is minus Q here and multiplied, plus 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, Q1 Q2. If Q1 is your plus Q, Q2 is minus Q, and the separation between them is 2A. So your equation becomes, that is, here the term will be negative, so I took Q common, so V1 minus V2 whole multiplied with Q minus, this term will be negative, will come here, Q square by 4 pi epsilon naught into 2A. Now, let us evaluate the value of V1 minus V2. V1 minus V2 is the potential difference between these 2 points. V1 is the potential here and V2 is the potential at this point. Now, we can use this equation like it is the relation between electric field and potential difference. Is equal to minus dV by dr. Already we have derived. Now, you see this dV is what? The potential difference between this point and this point. So, this is minus V1, that is minus of V1 minus V2. What is this dr? Dr is what? Try to understand. While calculating this distance, we need to take the perpendicular distance between, or the displacement of the charges. Displacement of the charges in what? The opposite to the electric, that means parallel to your electric field. Or this distance we can get to know in some Latin instant, like this is what? This is the perpendicular distance between two equipotential surfaces that I have marked here. This one and this one are two equipotential surfaces. I will tell later what is an equipotential surface. So that gap, the perpendicular gap between these two, we can calculate here. See, this is the dipole moment here, and this, let's say this is the direction of electric field and the angle between them is theta. Now, parallel to the electric field, this gap will be, if this is 2A and this is theta, then this will be your 2A cos theta. So which will be your dr. So E is equal to minus V1, this V1 minus V2 by 2A cos theta. Now we can get what? V1 minus V2. So your V1 minus V2 will be, just multiply and the negative sign. So V1 minus V2 is equal to minus E into 2A cos theta. Now I can put the value of V1 minus V2 here. U is equal to minus E into 2A cos theta into Q. And see here, Q into 2A. Q into 2A will be your dipole moment. Q into 2A will be your dipole moment. And this term is just repeated here. Now your expressions will be E, Q into 2A is P, means it is minus PE cos theta, and this term is minus Q square 4 pi epsilon 2A. See, this is one constant which will be occurring in your expressions of the potential energy, and we know any constant term that appears in the expression of potential energy, it is just irrelevant. It is irrelevant, or it is undesired term. It has insignificant here. So if you can drop it, if you drop this term, so your expressions will be similar, means u is equal to minus PE cos theta. Clear? U is equal to minus PE cos theta is what the expression for potential energy of an electric dipole at a position theta, means theta is angle between P and E. Clear? Here, let me explain you three important points. Like, just one point already have discussed. See, case already pi is your already have discussed it. Theta is equal to pi by 2. This is called your zero energy position. Clear? Now let us discuss the theta is equal to 0 degree. If theta is equal to 0 degree, means the electric field and dipole moment, they are parallel to each other. At this position, the torque on the dipole is PE sin theta, which is PE sin 0, which is equal to 0. And the force on the dipole is also 0 at this position. Force on the dipole is also 0. And the potential energy of the dipole, U is minus PE cos theta, which is minus PE cos 0. So, U is equal to minus PE. So, this is a case for when theta is equal to 0 degree. Actually, this theta 0 position is called your stable equilibrium position. This position is called stable equilibrium position because suppose from this position, if you rotate the dipole or slightly disturb it, it will try to comes back to its original position if it is slightly disturbed from its original position. Let me explain it once again. If from the stable equilibrium position, means theta is equal to 0 degree, if you rotate the dipole in either direction, after certain oscillations like this, the dipole will comes to rest in its previous desired position. Theta is equal to 0 degree. That's why it is called your stable equilibrium position. Under this position, F is equal to 0, your torque is equal to 0, and your potential energy is minimum. Clear? Now, the second case, theta is equal to 180 degree. In theta is equal to 180 degree, also the force is equal to 0 and torque, as the formula for torque is equal to P is sin theta, sin 180 is also 0, then torque is also 0, and in the case of your potential energy, which is minus PE cos theta, theta is equal to 180 degree, means cos 180 is your minus 1, that I can write minus PE, which is minus 1, which is your plus PE. So, this theta 180 position, it is called unstable equilibrium. Unstable equilibrium. Why unstable equilibrium? See, suppose electric field is in this direction and dipole moment is in this direction. Suppose if a dipole is placed by making an angle of 180 degree in unstable equilibrium position, if you slightly disturb, see at this position force 0, torque 0. At this position if you slightly disturb, it won't come back to its original position, which is theta is equal to 180. It will rotate and it will be coming, it will comes to your stable equilibrium position. That's why this position is unstable. Why? Because earlier, means theta 180 degree position, it is stable. If you slightly disturb, it will be at theta is equal to 180 degree position, force 0, torque 0. It will be remain as it is if it is undisturbed. But if you disturb it, it will comes back to this position. That's why this equilibrium is called unstable equilibrium, and in this case, remember, the potential energy here it is maximum. The potential energy here it is maximum, and in your case, if your stable equilibrium, this potential energy will be minimum for case of your stable equilibrium. So try to remember this. This is most important part here. Now students, let me explain you the equipotential surfaces and its properties. That I have just now I have said what is equipotential surfaces. See, these are the surfaces actually. These are the surfaces. If you take any 2 points on the surfaces, the potential at the 2 points are equal. Or if you take any point, any 2 points on the surfaces, the potential difference between the 2 points is 0. So that's what I have written here. These are the surfaces where at each and every point the electric potential have the same value. So what I have taken, I took a surface here 1, 2, 3, 4 like. So means n number of points you can take. So at each and every point the potential are equal. Means V1, V2 is equal to V3 is equal to V4. All are equal. If you take the difference between potential, then it will be your 0. Clear? Now these are the properties of electric potential. The first property is no mark is done in moving a charge on an equipotential surface. Why so? Because according to our formula for work done, it is nothing but the potential difference between these 2 points multiplied with the charge which is taken from one point to the other. Are you getting my point? Suppose you are taking a charge Q from point 2 to point 1. So your volume will be how much? Suppose here it is point 1 and here it is point 2, and these 2 points are located on an equipotential surface. V1 is the potential at point 1, V2 is the potential at point 2. Clear? So you are taking this charge from 2 to 1. So your work done will be how much? The potential here minus the potential here. Means V1 minus V2 multiplied with the charge. So W is equal to VQ formula. Now as these 2 points are located on the equipotential surface, so V1 minus V2 is equal to 0. So 0 into Q is equal to 0. So this is the first point. Now comes to your second point. Electric field. So electric field is always perpendicular to the equipotential surface. Suppose you take a surface here. Electric field is always perpendicular to the equipotential surface. It is given. Why? If not so, then what would have happened? Suppose the electric field is not perpendicular. Let's say this is the direction of electric field and this is your equipotential surface. And let's say the angle between them is theta. This means this line is lying on the surface itself. So electric field is making an angle theta with your equipotential surface. Clear? So I can resolve this electric field into 2 components. One along the perpendicular and one parallel to the surface. So because of this parallel component of the field, if you move a charge between these 2 points, this electric component will exert force. Force into displacement will be definitely some amount of work will be there. But just now, what in the first point, no work is done in moving a charge. So this, if electric field won't be perpendicular, then this 2 points would be contradictory. That's why there would not be any parallel component. So the only component will be what? If this will be the surface, it will be your normal component. Means this equipotential surface and electric field, they are perpendicular to each other. Try to understand it. Then third point, they won't intersect. Simple point. If they intersect at the point of intersections or at the regions of intersections, there will be n number of values of your electric potential. Also electric field, which is a contradictory statement, because at a particular point, that point must have a single value of electric potential as well as electric field. That's why they won't intersect. Clear? They are closer, means equipotential surfaces are closer where electric field is more, and vice versa. Means what? If the electric field is strong, then the equipotential surfaces are closer in that region, and if the electric field is weaker, then the electric field will be, your equipotential surfaces will lie far apart. Means what? Suppose this we can know from this expression, E is equal to minus of dV by dr. See, dV is what? Suppose dV is actually the potential difference between 2 equipotential surfaces. Let's say this is one equipotential surface, here is another equipotential surface, here it is another equipotential surface. Let's say another equipotential surface here. All these surfaces, let's say the value here it is V, here it is 2V, here it is 3V, here it is 4V. Is it clear? According to our definition, electric field is directed in the direction of decreasing potential and also perpendicular to the equipotential surface. So let us draw a line which must be perpendicular to all the surfaces like this. So this is the direction of electric field, and see, the direction of electric field is in the direction of decreasing potential. See here, this 4, 3, 2 and 1 volt. Clear? This is the direction of decreasing potential, so I am putting an arrow mark here. So this is the direction of electric field, and this is also normal to the equipotential surface. See, all the potential surfaces, they are separated here by 1 volt gap. But try to understand here, just see the gap here. Just see the gap here, and you see the gap here. Gradually, all of you just see here, the same two equipotential surfaces, the difference between their potential is 1 volt, but the gap is very less. Here, again between these two, there is a 1 volt potential difference, but the gap is slightly more than the previous one. Let's say if this is x, this will be 2x, and let's say this is 4x. So and see, try to understand here, since this region, the two equipotential surfaces are closer, means at this region the value of the electric field is more in comparison to that of the field at this region, because electric field is directed in the direction of decreasing potential, and the equipotential surface, the closer the equipotential surfaces will give you the higher value of your electric field. That this point is explaining. Is it clear? Okay. Now let us move to some shapes of your equipotential surfaces. Basic your shapes of equipotential surfaces of some charge and charge system. Suppose, let us take a point charge Q. Let us take a point charge Q. For a point charge, your equipotential surface shape we need to determine. For a point charge at a distance, some distance, let's say r, the value of the potential V is given by 1 by 4 pi epsilon naught, that is Q by R. It is the formula for your potential because of a point charge. It is clear, for a particular charge, the magnitude of Q is fixed. 4 pi epsilon naught value is also fixed. Means V will be constant at a particular point at a particular distance. So from a point charge at a particular distance, the value of V is fixed. Means if you take a charge here, R, let's say the charge is Q here. By taking a charge Q and by choosing some distance, let's say R, if I draw a sphere, try to think, the sphere's surface is all the time is at a distance R from the center. Means the surface and the distance between the surface and the center is always fixed, which is R here. Means on the surface, the value of V or potential for a point charge is always fixed. It means the shape of equipotential surface for a point charge is spherical. Clear? Means, and another interesting part is here, and we know the electric field lines for a point charge. Like, let us draw concentric spheres. Let us draw concentric spheres. If you draw concentric spheres, see, all the spheres are concentric because their center is 1, and let's say the radius here is R1. For this sphere, the radius is R2, and for this sphere it is R3, and the big sphere is R4, and at the center a charge is Q is located. Let's say, I don't know, let's say the charge may be positive, may be negative. If the charge is positive, let's say, suppose the charge here, it is a positive charge. For a positive charge, we know the electric field is directed away from the positive charge. Clear? So means this is the direction of electric field. This is the direction of electric field. Clear? And for a point charge, the value of the potential is given by this formula. V is inversely proportional to your R. Means where the R is more, the value of V will be less. Try to understand here. Clear? Where the value of R is more, V is less. So means, suppose I am marking the point here 1, this is 2, this is 3 and this is 4. 1, 2, 3, 4. Here, try to understand. Here on the surface of the first sphere, the potential has a unique value. Let's say it will be having value V or V1. On the surface of 2, let the value will be V2. On the surface of the 3, let the value be V3. And surface 4, it will be V4. Try to understand it. It's a very important part. Now, as for surface number 1, for the sphere number 1, the radius is the least one here. So its potential is maximum. Means the potential on the first sphere surface is maximum, then it is V2, then it is V3 and the least will be V4. Clear? Because as the sphere's radius are increasing, the value of the potential is decreasing, and we know the direction of the electric field is in the direction of decreasing potential. Is it clear? So this can be a very interesting and also an important question can be asked from here. Clear? All of you just check here. I have drawn here. See, this surfaces, they are closer because it represents stronger field, and gradually the separation gap between the surfaces I have just made wider because gradually the strength of the field is also decreasing. So question can come, draw equipotential surfaces for a single point charge and also explain its shape. Clear? So this is the shape of your positive charge. Similarly, you can take it for a negative charge. You can draw it for a negative charge, but the only difference is what? For a negative charge, you know, just the opposite. Electric field is directed inward. Electric field is directed inward. Means here just the opposite. Means the outer region sphere will be smaller. The gap between the spheres will be in the outer region will be smaller than that of the inner one. Clear? Now the second set of equipotential surface, all the time it is necessary. Like suppose for a uniform electric field, suppose you have given a uniform electric field. For a uniform electric field, remember the equipotential surfaces are all the time, these are parallel planes and equispaced. For uniform electric field, let's say the field is uniform here. For uniform electric field, if it is V, you can take it as, let's say, if it will be 3V, this will be 2V and this will be V. Gradually the potential is decreasing, but you see here, if the gap is X here, the gap is X here too, because the field is uniform. So this way, this is one equipotential surface where each and every point of the surface, the potential is 3 volt. Here the potential is 2 volt. Here the potential is V volt. But the gap between them is equal. Means if it is X, if it is X2. Clear? So these are some most important points. Similarly, you can, by applying some logic, you can draw equipotential surfaces for two charge system. For an electric dipole, you can take the reference of your book and you can see the diagram by applying a similar kind of logic there. Try to understand it.